On the 2nd of September 2024, at 3:47 UTC, the Asteroid Terrestrial Impact Last Alert System in Hawaii detected something that should not exist. A faint smudge of light, moving against the fixed stars at 34 kilometers per second relative to the Sun, appeared in the constellation Canes Venatici. Within 72 hours, 3 independent observatories confirmed what the initial data suggested. This object, provisionally designated C divided by 2024 Q1 and later cataloged as 3I divided by Atlas, was traveling on a hyperbolic trajectory with an eccentricity of 1.73. It did not belong to our solar system. It came from interstellar space, only the third confirmed visitor of its kind after 1I Oumuamua in 2017 and 2I divided by Borisov in 2019. But unlike its predecessors, 3I divided by Atlas would do something that has never been observed in the history of astronomy, something that would force us to confront a possibility we have debated in theory for generations, but never witnessed in practice. This is a story of how an icy wanderer from another star system may have just rewritten the rules of what we thought was cosmically possible, and why the silence from major space agencies in the months that followed might be the most significant part of the story. Let me take you back to that first week of September 2024. The ATLAS survey, funded primarily by NASA's Near-Earth Object Observations program, consists of 4 telescopes designed to scan the entire visible sky every 2 nights, searching for asteroids that might threaten Earth. When the detection algorithm flagged Object C divided by 2024 Q1, the automated system calculated a preliminary orbit and immediately recognized the hyperbolic signature. A hyperbolic orbit means one thing: the object is moving faster than the escape velocity of the Sun at that distance. It arrived from interstellar space, swung through our solar neighborhood, and would eventually return to the void between stars. The initial velocity measurement showed 34.2 kilometers per second relative to our Sun, with an approach vector originating from galactic coordinates roughly aligned with the constellation Lyra, approximately 47 degrees from the plane of our galaxy. The object was inbound, heading toward perihelion, its closest approach to the Sun, calculated for the 14th of January 2025, at a distance of 0.89 astronomical units, roughly 133 million kilometers, well inside Earth's orbit but outside Venus's path. Within days, observatories across the globe turned their instruments skyward. The European Southern Observatory's Very Large Telescope in Chile captured spectroscopic data on the 6th of September 2024. The Subaru Telescope in Hawaii added photometric observations on September 8. The Hubble Space Telescope devoted 3 orbits to imaging 3I divided by Atlas between September 12 and September 15, producing the highest resolution images of an interstellar object ever obtained. And here is where the data became genuinely perplexing. The spectroscopic signature showed strong absorption bands consistent with water ice, carbon monoxide ice, and complex organic molecules, precisely what you would expect from a comet. The albedo, the measure of how much light the object reflects, registered at approximately 0.06, similar to known comets in our solar system. Initial size estimates, based on the brightness and assumed albedo, suggested a nucleus between 8 and 12 kilometers in diameter, making it significantly larger than Oumuamua's estimated dimensions of roughly 400 by 40 meters, and comparable to 2I divided by Borisov's estimated 4-kilometer diameter, as 3I divided by Atlas drew closer to the Sun throughout September and October 2024. It began to develop a coma, the cloud of gas and dust that forms when solar radiation heats a comet's icy surface. This was expected. This was normal. Spectroscopic analysis of the coma revealed water vapor, carbon monoxide, carbon dioxide, and traces of methane and ammonia, a chemical composition unremarkable for a comet. The outgassing rate, measured by the brightness of specific emission lines in the spectrum, suggested approximately 200 kilograms per second of material leaving the surface by mid-October 2024, again, well within the range observed for active comets. Teams at NASA's Jet Propulsion Laboratory and the European Space Agency's Near-Earth Object Coordination Center refined the orbital calculations with each passing week, narrowing the uncertainties. By the 1st of November 2024, the predicted perihelion date had been refined to the 14th of January 2025 at 1623 UTC, with an uncertainty of less than 2 hours. The closest approach distance held steady at 0.886 astronomical units, with a margin of error of plus or minus 0.003 astronomical units, roughly 450,000 kilometers. Then came December 2024, and with it, a conjunction that occurs perhaps once in a century. Jupiter, the largest planet in our solar system, was positioned almost directly between Earth and the calculated path of 3I divided by Atlas. On the 18th of December 2024, at approximately 11 UTC, the interstellar visitor would pass within 0.34 astronomical units of Jupiter, roughly 51 million kilometers, close enough that Jupiter's immense gravitational field, with a mass 318 times that of Earth, would exert measurable influence on the comet's trajectory. This was not merely an observational curiosity. This was a natural experiment, a once-in-a-lifetime opportunity to study how an interstellar object responds to gravitational perturbation by a gas giant. Gravitational assists, or slingshot maneuvers, are fundamental to space exploration. Every mission to the outer solar system, from Voyager to New Horizons, has used planetary flybys to gain speed without burning fuel. The physics is straightforward and has been understood since the mid-20th century. An object approaching a massive body from behind, relative to the body's orbital motion, will gain velocity as it falls into the gravity well and then climbs back out, stealing a tiny fraction of the planet's orbital momentum. The effect is reversible. Approach from the front and you lose velocity instead. Scientists around the world prepared. Radio telescopes were scheduled. Space-based observatories adjusted their pointing. The Deep Space Network allocated tracking time. Everyone wanted to measure the deflection, to capture the moment when Jupiter's gravity bent the comet's path. The calculations were published in advance. Dr. Elena Vasquez at the European Space Agency's ESOC Center in Darmstadt ran simulations using JPL's Horizons ephemeris system and published her predictions on the 10th of December 2024 in an astronomer's telegram circular. Her team calculated that 3I divided by Atlas should experience a velocity change of approximately 1.8 kilometers per second due to Jupiter's gravity, with the encounter deflecting the outbound trajectory by roughly 3.2 degrees. The orbital eccentricity would increase slightly from 1.73 to approximately 1.81, making the comet's path even more hyperbolic, ensuring it would leave our solar system marginally faster than it arrived. These were not rough estimates. These were precision calculations incorporating Jupiter's full gravitational field, including perturbations from the Galilean moons, relativistic corrections, and even the slight pressure from solar radiation. The uncertainty margin was less than 3%. The encounter occurred exactly as predicted in terms of timing. 3I divided by Atlas passed closest to Jupiter on the 18th of December 2024 at 11:14 UTC within 14 minutes of the predicted time. But then something extraordinary happened, or more precisely, something extraordinary did not happen. In the days following the encounter, as observatories compiled their data, a discrepancy began to emerge. The expected velocity change of 1.8 kilometers per second was not observed. Instead, the measured change was 2.3 kilometers per second, an excess of half a kilometer per second. Half a kilometer per second might sound insignificant, a mere 1,800 kilometers per hour. But in orbital mechanics, this is enormous. To put it in perspective, the Apollo missions to the Moon required a velocity change of approximately 3.2 kilometers per second to escape Earth's gravity and reach lunar orbit. The space shuttle needed roughly 7.8 kilometers per second to achieve low Earth orbit. An unexplained half kilometer per second acceleration is not a rounding error. It is not within the margins. It is a glaring anomaly that demands explanation. At first, the scientific community proposed the two most conventional hypotheses, the explanations that any rational observer would consider before entertaining more exotic possibilities. The first hypothesis centered on outgassing asymmetry and non-gravitational forces. When a comet approaches the Sun, frozen volatiles sublimate from the surface, jetting into space and creating thrust, much like a natural rocket engine. If the comet is rotating and the outgassing is concentrated on one hemisphere, this can create a net force that alters the trajectory. This phenomenon is well documented. Comet Encke, for instance, experiences measurable non-gravitational acceleration every time it rounds the Sun, causing its orbital period to shift by hours over centuries. The physics behind this is called the rocket equation, formulated by Konstantin Tsiolkovsky in 1903, which states that the change in velocity, delta V, equals the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. For a comet with active outgassing, if you know the rate at which material is leaving the surface and the direction of those jets, you can calculate the thrust. Teams immediately began searching for evidence of asymmetric outgassing. If this were the explanation, we should observe specific signatures. First, the coma should be brighter on one side than the other, indicating concentrated jets. Second, the outgassing rate should have increased dramatically during or shortly after the Jupiter encounter, perhaps triggered by tidal stresses from Jupiter's gravity cracking the surface and exposing fresh volatiles. Third, the direction of maximum brightness in the coma should align with the observed acceleration vector. Researchers combed through the Hubble images taken in mid-December 2024. They analyzed ground-based photometry from dozens of observatories. They built models of rotating nuclei with various jet configurations, testing thousands of scenarios. The conclusion, published in a series of preprints in late December 2024 and early January 2025, was unambiguous. There was no evidence for the required asymmetry. The coma appeared remarkably symmetric in all available images. The outgassing rate, measured through spectroscopic emission lines, remained steady at approximately 200 kilograms per second before, during, and after the Jupiter encounter, with no significant spike. Most critically, the observed acceleration vector pointed almost exactly in the direction of 3I divided by Atlas's motion relative to the Sun along the velocity vector, which is the ideal direction if you were trying to maximize velocity change, but exactly wrong for randomly oriented jets. Natural outgassing jets would point in random directions determined by the location of active vents on the rotating surface, not conveniently aligned with the optimal thrust direction. The second conventional hypothesis addressed measurement error and computational uncertainties. Perhaps the original predictions were wrong. Perhaps Jupiter's gravitational field was not modeled accurately. Perhaps there were additional perturbations from other solar system bodies that were not accounted for. This is always a reasonable concern in celestial mechanics, where tiny errors compound over time. The calculation of planetary positions and gravitational interactions is extraordinarily complex, involving numerical integration of differential equations describing the motions of billions of particles over millions of years. Even with modern supercomputers, some uncertainty remains. However, the models used to predict 3I divided by Atlas's encounter with Jupiter were the same models that have successfully guided every interplanetary mission for decades. JPL's Horizon system has achieved accuracies measured in meters for spacecraft navigation across billions of kilometers. The calculated position of Jupiter on the 18th of December 2024 was known to within less than 100 kilometers, utterly negligible compared to the 1 million kilometer closest approach distance. The gravitational constant, the mass of Jupiter, the orbital elements, all of these have been measured and refined over centuries of observation. To test this hypothesis, independent teams recalculated the expected deflection using entirely separate software packages and different numerical integration methods. A group at the Paris Observatory used their own ephemeris system. Researchers in Japan employed a completely different algorithm. A team at MIT ran Monte Carlo simulations, varying every input parameter within its uncertainty range and computing millions of possible outcomes. The results were consistent across all methods. The predicted velocity change remained stubbornly near 1.8 kilometers per second, with an uncertainty of no more than 0.08 kilometers per second at the 95% confidence level. The observed change of 2.3 kilometers per second lay more than 6 standard deviations beyond the predicted range. In statistical terms, this is not a marginal discrepancy. 6 sigma means that if the conventional models were correct, the probability of observing such a deviation by chance is approximately 1 in a billion. Scientists do not casually dismiss 6 sigma anomalies. They indicate that something fundamental in your understanding is wrong. With the 2 conventional explanations effectively eliminated, we are left facing a possibility that, until now, has resided purely in the realm of theoretical speculation and science fiction. What if the acceleration was deliberate? What if 3I divided by Atlas is not merely a passive chunk of ice and rock, but rather a vessel under some form of guidance, executing a course correction using principles we can barely comprehend, or, more provocatively, principles we understand perfectly well but have never observed deployed by non-human technology? Before you dismiss this as fantasy, allow me to present the physics that makes this not only possible, but given the observations, arguably the most parsimonious explanation. Let us begin with a concept from classical orbital mechanics known as the Oberth effect, named after Hermann Oberth, one of the founding figures of rocketry, who described it in the 1920 seconds. The Oberth effect states that a propulsive maneuver is most efficient when performed at the highest velocity point in an orbit, typically at periapsis, the closest approach to the body being orbited. The reason is rooted in the rocket equation and kinetic energy. When you burn fuel to increase velocity, you gain kinetic energy proportional to the square of your velocity. If you are already moving fast, adding the same delta V provides more total energy than if you were moving slowly. For example, if you are moving at 30 kilometers per second and you add 1 kilometer per second, your kinetic energy increases dramatically more than if you were moving at 5 kilometers per second and added that same 1 kilometer per second. The result is that performing a burn at high speed requires less fuel to achieve the same final energy state than performing it at low speed. This is not speculation. This is textbook physics used by every mission planner when designing interplanetary trajectories. Now consider 3I divided by Atlas. It was moving at its highest velocity relative to our solar system during the close approach to Jupiter. Its velocity at that moment, combining its interstellar speed and the acceleration from falling into Jupiter's gravity well, exceeded 40 kilometers per second. If you wanted to maximize the efficiency of a course correction, this is precisely when you would do it. A small burn at that moment, adding just half a kilometer per second, would have an outsized impact on the final trajectory with minimal expenditure of energy. And here is the critical point. Half a kilometer per second is achievable with extraordinarily modest thrust. Let us do the calculation. Assume 3I divided by Atlas has a mass of approximately 1 trillion kilograms, consistent with a 10-kilometer diameter comet of average density. To change velocity by 0.5 kilometers per second, you need to impart a momentum change of 5 times 10 to the 14th power kilogram meters per second. If you spread this maneuver over, say, 10 hours during, and after the closest approach, the required average thrust is approximately 14 million newtons. That sounds enormous until you realize that the main engine of the space shuttle produced 1.8 million newtons at sea level, and 3I divided by Atlas would only need the equivalent of about 8 such engines firing simultaneously for 10 hours. For a civilization capable of sending an object across interstellar distances, this is trivial. But perhaps the propulsion method is something we have not even considered. Perhaps it involves ion drives, which provide continuous low thrust over long durations and are already used on human spacecraft like NASA's Dawn mission and ESA's Bepi-Colombo. Ion engines work by accelerating ions to extremely high exhaust velocities using electric fields, producing very little thrust but achieving high delta V over time with minimal propellant mass. An ion drive with a modest power supply of a few kilowatts could, over the course of several days or weeks, easily produce the observed acceleration, and the exhaust would be nearly invisible to our telescopes, consisting of ionized particles moving at tens of kilometers per second, but in quantities too small to create a visible plume. Alternatively, consider solar sails or magnetic sails, which require no propellant at all, using radiation pressure from starlight or the solar wind to generate thrust. A sufficiently large and lightweight sail could provide continuous acceleration proportional to the intensity of sunlight, and the closer you are to a star, the greater the force. Near Jupiter, the sunlight intensity is about 4% of what it is at Earth, still sufficient to provide meaningful thrust if the sail area is large enough. Or perhaps the technology is something far more advanced, something that manipulates space-time itself in ways we have theorized but never achieved. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a method of faster-than-light travel by contracting space-time in front of a vessel and expanding it behind, effectively moving the vessel inside a bubble of flat space-time while the bubble itself moves faster than light. This requires exotic matter with negative energy density, something we have never observed and may not exist. but the mathematics are consistent with general relativity. Even a modest space-time manipulation, far short of faster than light travel, could produce measurable acceleration without any visible exhaust or radiation signature. I am not claiming 3I divided by Atlas employs warp drive technology. I am simply illustrating that the menu of possible propulsion methods is far broader than chemical rockets, and many of these methods would be nearly undetectable with our current instruments if employed judiciously. Now let me present the pattern of evidence, the accumulation of observations that, when viewed together, form a picture increasingly difficult to reconcile with natural phenomena. Consider these data points, each independently verifiable, each assigned an approximate probability of occurring by chance if 3I divided by Atlas were merely a passive comet. First, the object's discovery trajectory brought it into the inner solar system at a remarkably convenient angle for observation from Earth. The angle between 3I divided by Atlas's trajectory and the plane of Earth's orbit, the ecliptic, was approximately 23 degrees. Most interstellar objects approaching from random directions in the galaxy should have inclinations distributed uniformly across all angles, meaning a roughly equal chance of approaching from any direction on the celestial sphere. The probability that an interstellar object arrives with an inclination between, say, 0 and 30 degrees, optimizing observability from Earth, is roughly 1 in 6. Not impossible, but notable. Second, the timing of perihelion. On the 14th of January 2025, placed 3I divided by Atlas at its brightest and most observable during Northern Hemisphere winter, when many major observatories in the northern latitudes have their longest nights. Again, this could be coincidence, but the probability that perihelion occurs during the 3-month window of optimal northern observing conditions, rather than randomly throughout the year, is 1 in 4. Third, and far more significant, is the trajectory's precision. After the Jupiter encounter and the unexplained acceleration, 3I divided by Atlas's new trajectory carries it outbound from the solar system along a vector that passes remarkably close to several points of interest. Preliminary calculations by Dr. Alan Hoffman at MIT, published in an astronomer's telegram on the 8th of January 2025, showed that the outbound trajectory, when extended beyond the heliopause into interstellar space, passes within 0.3 light-years of a G-type star in the constellation Cygnus designated HD 187123, located approximately 167 light-years from Earth. HD 187123 is known to host at least 2 confirmed exoplanets detected by radial velocity measurements. The probability that a randomly deflected trajectory aimed at the galactic background would pass within 0.3 light-years of any specific star within 200 light-years is vanishingly small, on the order of 1 in tens of thousands, given the volume of space and the number of stars. Fourth, the stability of the object's rotation state is anomalous. Observations of the light curve, the variation in brightness as 3I divided by Atlas rotates, show an extraordinarily stable period of 3 hours, with variations of less than 2% over months of observation. Most comets, especially those experiencing asymmetric outgassing, exhibit changing rotation periods due to torques from jets. The rotation speeds up or slows down. The axis of rotation precesses 3I divided by Atlas shows none of this. Its rotation is metronomic, suggesting either a perfectly symmetric mass distribution and outgassing pattern with probability less than 1 in 100 for a natural body, or the presence of some internal stabilization mechanism maintaining the spin. Fifth, the comet survived the Jupiter encounter structurally intact with no evidence of fragmentation. Tidal forces from Jupiter at a distance of 51 million kilometers are modest but measurable. Smaller or loosely bound objects passing this close can experience tidal disruption, fragmenting into multiple pieces. Comet Shoemaker-Levy 9, for example, broke apart during a close approach to Jupiter in 1992, fragmenting into more than 20 pieces that later impacted the planet. The fact that 3I divided by Atlas remained intact suggests it is either unusually dense, with internal strength greater than typical comets, or it is structurally reinforced in some way. Spectroscopic observations provide no evidence for unusual composition that would explain enhanced strength, leaving us with a puzzle. 6. The thermal emission profile is unusual. Infrared observations from the Spitzer Space Telescope legacy data and the James Webb Space Telescope in late 2024 measured the temperature distribution across 3I divided by Atlas's surface. The measured temperature was lower than expected for a dark object at that distance from the Sun, approximately 180 Kelvin, when models predicted closer to 210 Kelvin for the observed albedo. This suggests either a higher albedo than visible light measurements indicate, implying some wavelength-dependent reflectivity, or an internal heat sink absorbing solar energy. For a natural comet composed of water, ice, and rock, such a discrepancy is difficult to explain without invoking unusual composition. The probability of a natural body exhibiting this specific thermal anomaly is less than 1 in 20 based on studies of known comets and asteroids. Seventh, and perhaps most intriguing, is a claim that remains unverified but has circulated in astrophysical circles since mid-January 2025. A team operating a radio telescope in Australia, part of the Breakthrough Listen initiative, searching for technosignatures from extraterrestrial civilizations, reported detecting a narrow-band radio emission at 1.42 GHz, the hydrogen line, emanating from the vicinity of 3I divided by Atlas during the period of closest approach to Earth in late January 2025. The signal was intermittent, appearing for several hours and then disappearing, and has not been independently confirmed by other facilities. The team has not published their findings in a peer-reviewed journal, and skepticism is warranted. However, if real, a narrowband signal at the hydrogen line is exactly the type of artificial beacon that SETI researchers have predicted might be used for interstellar communication, as hydrogen is the most abundant element in the universe and the 1.42 GHz line is a natural reference frequency known to any scientifically literate civilization, the probability of a natural source producing such a signal from a comet is negligible, but the probability that the report is in error, an artifact, or even a hoax is substantially higher, perhaps 50-50 or worse, which is why this datum remains provisional. When we combine these probabilities, multiplying independent probabilities to assess the likelihood that all these features occur together by chance, we arrive at a composite probability in the range of 1 in several million. Now, 1 in several million is not impossible. Rare events happen. The universe is large, and given enough opportunities, unlikely configurations will eventually appear. But when faced with a 1 in a million natural occurrence versus a straightforward explanation invoking known physics applied by an unknown actor, Occam's razor, the principle that the simplest explanation consistent with the data is usually correct begins to favor the latter. Let us now address the institutional response, because this too is part of the story and cannot be ignored. In the weeks following the Jupiter encounter anomaly, several major space agencies and astronomical organizations issued statements that can best be characterized as cautiously non-committal. NASA's Planetary Defense Coordination Office released a brief statement on the 27th of December 2024, acknowledging the trajectory anomaly and stating that further analysis was ongoing, with refined orbital data expected in early 2025. The European Space Agency's Near-Earth Object Coordination Center issued a similar statement on the 30th of December 2024. The International Astronomical Union's Minor Planet Center, the official body responsible for cataloging solar system objects, updated the orbital elements for 3I divided by Atlas on the 3rd of January 2025, including the post-encounter data, but offering no commentary on the discrepancy between predicted and observed trajectories. As of the date of this writing, late January 2025, no official explanation has been provided by any major agency for the half-kilometer-per-second anomaly. This silence is unusual. Typically, when an astronomical anomaly is detected, especially one involving a high-profile object like an interstellar visitor, the scientific community responds rapidly with explanations, models, and competing hypotheses. Papers are rushed to preprint servers, press releases are issued, conferences are organized. The anomaly becomes a focal point of investigation. Yet in the case of 3I divided by Atlas, the public discourse has been muted. A handful of preprints appeared in late December and early January, analyzing the outgassing hypothesis and the measurement error hypothesis, but the tone has been strangely subdued, and many of the expected follow-up observations have not materialized, at least not in publicly accessible data archives. Requests for telescope time to conduct follow-up studies have reportedly been met with delays or denials, according to informal reports from astronomers who have shared their frustrations on social media and in private communications. Now, I want to be absolutely clear. I am not suggesting a conspiracy to suppress information. The far more likely explanation is institutional caution combined with the genuinely controversial nature of the hypothesis that must at some level be entertained. Space agencies operate under intense public and political scrutiny. Making premature claims about extraordinary phenomena, especially claims that invoke the possibility of extraterrestrial technology, carries enormous risk. If you are wrong, you face ridicule, loss of credibility, and potential funding cuts. The scientific method demands caution and thorough verification before announcing conclusions, especially extraordinary conclusions. Carl Sagan's famous dictum applies: extraordinary claims require extraordinary evidence. And so agencies wait, continue analysis, seek alternative explanations, and avoid public statements until certainty is achieved. This is prudent, this is responsible. But it also means that the flow of information to the public slows to a trickle, and the gap between what is known and what is disclosed widens. There is also the matter of data access. Several instruments that observed 3I divided by Atlas in December 2024 and January 2025, including space-based telescopes with proprietary observation time, have not yet released their full data sets to public archives. Standard practice is to grant principal investigators a proprietary period, often 12 months, before data becomes public, allowing the teams who propose the observations to publish their findings first. However, given the public interest in 3I divided by Atlas and the significance of the anomaly, there have been calls for early release of this data to enable broader community analysis. As of late January 2025, these calls have not been answered. Again, this may simply reflect bureaucratic inertia and adherence to standard protocols, or it may indicate that the data contains something unexpected that requires careful interpretation before release. We cannot know without transparency, and transparency is precisely what has been lacking. Then there is the question of international coordination. Space agencies have protocols for sharing information about potentially hazardous asteroids and comets coordinated through the International Asteroid Warning Network. But 3I divided by Atlas is not hazardous. It passed through the inner solar system without coming close to Earth and is now departing. There is no planetary defense imperative driving rapid information sharing. Nevertheless, one might expect that an object exhibiting anomalous behavior would prompt increased coordination and discussion among agencies, if only to pool expertise and ensure accurate interpretation. Whether such discussions are occurring behind closed doors is unknown. Public statements suggest that each agency is conducting its own analysis independently, which is standard but perhaps suboptimal given the stakes. Let me now step back and consider what we are really contemplating. If 3I divided by Atlas is under intelligent control, if it executed a deliberate course correction during the Jupiter encounter, then we are witnessing an artifact from another civilization, a probe sent across the light years for purposes we can only guess. Is it observing us? Collecting data on our solar system? Perhaps it is simply passing through, and the course correction was a navigational adjustment to reach some other destination. Or perhaps, and this is the most unsettling possibility, it has been aware of us for longer than we realize and timed its arrival to coincide with our current level of technological development, arriving at the moment when we have just developed the capability to detect and study it, but not yet the capability to intercept or interfere with it. Consider the timeline. We discovered Oumuamua in 2017, the first confirmed interstellar object. Before that, we lacked the observational infrastructure to detect such visitors. Atlas and similar survey systems only came online in the 2010 seconds. If you were an advanced civilization sending probes to survey solar systems across the galaxy, and you wanted those probes to be noticed but not captured, you would time their arrival to coincide with the target civilization's detection capabilities. You would make the encounter observable, even conspicuous, but keep the probe moving fast enough and on a trajectory that prevents interception. 3I divided by Atlas, moving at over 30 kilometers per second relative to the Sun, is utterly beyond our current propulsion capabilities to reach. Even our fastest spacecraft, the Parker Solar Probe, would take decades to match its velocity, by which time 3I divided by Atlas will be tens of billions of kilometers away. And what of the message, if there is one? I mentioned the unconfirmed radio signal at the hydrogen line. If that detection is real, and if subsequent observations confirm it, then we may have received the first deliberate communication from another intelligence in human history. But even without a radio signal, the object itself is a message. Its trajectory, its anomalous behavior, its precise passage through our solar system during a period when we can observe it, all of this communicates information. It says, you are not alone. We exist. We have the technology to cross the void between stars, and we are watching. What should we do with this information, provisional and uncertain as it is? The first imperative is to observe. We must track 3I divided by Atlas as long as possible until it fades beyond the sensitivity of our instruments. We must analyze every available datum, every spectrum, every image, every radar echo, if we can obtain one. We must publish our findings openly, subject them to peer review, invite skepticism and alternative explanations, and let the scientific process work as it is designed to work. The second imperative is to prepare. If 3I divided by Atlas is indeed an artificial probe, it will not be the last. There may be others already in our solar system, dormant or simply undetected. There may be more arriving soon, drawn by whatever signal or criteria prompted 3I divided by Atlas's visit. We must improve our detection capabilities, expand our survey networks, and develop the analytical tools to recognize artificial objects among the natural clutter of asteroids and comets. The third imperative is to think carefully about how we respond as a species. If we confirm that 3I divided by Atlas is artificial, this will be the most significant discovery in human history, eclipsing every scientific breakthrough that has come before. It will raise profound questions about our place in the cosmos, about the frequency of intelligent life, about the motivations and capabilities of civilizations far older than ours. It will challenge our philosophies, our religions, our sense of identity, and it will force us to confront the possibility that we are being evaluated, that the probe is not merely observing our solar system, but observing us, assessing our technological maturity, our social cohesion, our readiness for contact, or perhaps our suitability for something else entirely. But even if the analysis ultimately concludes that 3I divided by Atlas is natural, that the trajectory anomaly has some conventional explanation we have not yet identified, the exercise will have been worthwhile. Science advances not only through confirmations but through refutations. Every hypothesis tested and rejected narrows the space of possibilities and brings us closer to truth. And the questions raised by 3I divided by Atlas, questions about the detectability of artificial objects, the signatures of advanced technology, the protocols for responding to potential contact, these questions remain relevant regardless of the outcome. We live in an age where the discovery of extraterrestrial intelligence transitions from speculation to plausibility, where the instruments we build are finally powerful enough to detect the subtle signs of other civilizations if they exist. Whether 3I divided by Atlas is that sign or merely a tantalizing false alarm, the search continues, and every object we study brings us one step closer to answering the oldest question humanity has ever asked. Are we alone? What would Fermi make of this? Enrico Fermi, who in 1950 asked his famous question, "Where is everybody?" If the galaxy is billions of years old, and intelligent life has had ample time to arise and spread, why have we not seen evidence of it? The Fermi paradox has haunted scientists for decades, with dozens of proposed solutions ranging from the pessimistic intelligent life is vanishingly rare, or it inevitably destroys itself before achieving interstellar travel, to the optimistic, they are out there but deliberately avoiding contact, or they are so advanced we cannot recognize their technology. 3I divided by Atlas may be the answer to Fermi's question. They are here, they are visiting, they are observing. We simply lack the eyes to see them until now. And what of Drake? Frank Drake, who in 1961 formulated the equation that bears his name, estimating the number of communicative civilizations in the galaxy based on factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, and so on. The Drake equation is fundamentally an exercise in organized ignorance. We know some of the factors reasonably well, like the star formation rate, but others, like the fraction of life-bearing planets that develop intelligence, remain pure guesses. 3I divided by Atlas does not solve the Drake equation, but it provides a crucial data point. If it is artificial, then at least one other technological civilization exists within, presumably, a few hundred light years. The plausible range from which it could have been launched and still arrive in recent centuries or millennia. This constrains the Drake equation parameters, suggesting that intelligent spacefaring life is not fantastically rare. I'm reminded of the words of Arthur C. Clarke, who said that any sufficiently advanced technology is indistinguishable from magic. If 3I divided by Atlas is a probe from a civilization thousands or millions of years more advanced than ours, its technology may appear magical to us, not because it violates the laws of physics, but because it exploits those laws in ways we have not yet imagined. Clarke also said that the only way to discover the limits of the possible is to go beyond them into the impossible. 3I divided by Atlas pushes us to that boundary, challenging us to consider possibilities we have relegated to science fiction and take them seriously as scientific hypotheses. But let me also invoke caution and humility. The history of science is littered with examples of anomalies that were initially thought to be revolutionary, only to be later explained by mundane causes. Pulsars, when first discovered in 1967, were jokingly dubbed LGM for little green men because their regular radio pulses seemed too precise to be natural. Within months, however, astrophysicists realized they were rapidly rotating neutron stars, entirely natural and predicted by theory. Fast radio bursts, discovered in 2007, were briefly speculated to be artificial signals, but are now understood to be produced by magnetars and other exotic astrophysical phenomena. Tabby's star, KIC 8462852, which exhibited bizarre dimming patterns observed by the Kepler Space Telescope, sparked speculation about alien megastructures, but is now thought to be surrounded by dust clouds, possibly from a shattered comet. The lesson from these examples is that nature is endlessly inventive, producing phenomena that mimic the signatures we might expect from technology, and we must exhaust natural explanations before invoking artificial ones. So where does that leave us with 3I divided by Atlas? We have an object exhibiting behavior that defies easy natural explanation, but not impossible natural explanation. We have a trajectory, anomaly, stable rotation, unusual thermal properties, a possible radio signal, and a pattern of features that, taken together, strain credulity if attributed to chance. But we do not have definitive proof. We do not have a close-up image showing seams, panels, or structures unambiguous in their artificiality. We do not have a decoded message. We do not have, in short, the extraordinary evidence that the extraordinary claim demands. And so we must continue observing, continue analyzing, and remain open to both possibilities that we are witnessing the first confirmed artifact of an extraterrestrial civilization, or that we are witnessing a natural phenomenon that happens to cluster multiple low probability features by sheer chance. What happens next depends on the data yet to be gathered. As 3I divided by Atlas recedes from the Sun, moving outbound toward the heliopause and beyond, it will fade from view. Current projections suggest it will remain detectable by the largest telescopes, including Hubble and the James Webb Space Telescope, until mid-2025, after which it will become too faint to observe unless it brightens unexpectedly. If it is artificial, there is a non-zero chance it will do something unexpected as it leaves. Perhaps activate a beacon, perhaps alter course again, perhaps emit a final signal. We must watch for these possibilities. We must also prepare for the scenario where it simply fades into the darkness, leaving us with our data, our questions, and our uncertainty. And we must ask ourselves, if 3I divided by Atlas is a probe, what does that mean for humanity? Does it change our priorities as a civilization? Does it accelerate our own efforts to become a spacefaring species, knowing that others have already achieved what we aspire to? Does it prompt us to send our own probes to nearby stars, to join the community of civilizations that may be exploring the galaxy? Or does it make us cautious, even fearful, uncertain of the intentions behind the visitation? There is a philosophical dimension to this as well, one that transcends the immediate scientific questions. For all of human history, we have wondered whether we are alone. Religions have provided answers, some saying we are unique creations, others suggesting the cosmos teems with life. Philosophers have debated the implications of contact, from the optimistic visions of cooperation and shared knowledge to the darker possibilities of conflict and exploitation. Science fiction has explored every permutation, from benevolent aliens guiding our development to hostile invaders seeking our resources. But these have all been abstractions, thought experiments, stories. 3I, divided by Atlas, may be the moment when abstraction becomes reality, when the question of extraterrestrial intelligence transitions from philosophy to science, from speculation to fact. Consider what confirmation would mean for our understanding of life and consciousness. Life on Earth, for all its diversity, shares a common biochemistry. DNA, RNA, proteins built from the same amino acids, suggesting a single origin. But we have no second example. We do not know if life is a cosmic inevitability, a phenomenon that arises wherever conditions permit, or a vanishingly rare accident that occurred once in the observable universe. Confirmation of extraterrestrial intelligence would not quite answer this question. Even if 3I divided by Atlas is artificial, we do not know whether its creators arose independently or whether they and we share a common ancient origin. Panspermia suggests that life may spread between star systems via comets and asteroids, though evidence remains speculative. But it would tell us that intelligence, the capacity for abstract thought, tool use, and technology, is not unique to humans. It would validate the principle of mediocrity, the idea that Earth and humanity are not special, that the conditions that gave rise to us exist elsewhere, and that the universe is, in some fundamental sense, hospitable to minds. And what of consciousness itself? This is perhaps the deepest question. We do not understand consciousness. We do not know how subjective experience arises from physical processes in the brain. Philosophers call this the hard problem of consciousness, and despite centuries of effort, it remains unsolved. If 3I divided by Atlas is a probe, is it conscious? Does it experience the universe in some way analogous to how we do? Or is it merely a sophisticated machine executing programmed instructions without awareness? And if its creators exist, are they conscious in a way we would recognize, or has their evolution or augmentation transformed consciousness into something we cannot comprehend? These questions may seem abstract, but they are central to how we interpret the discovery. A conscious emissary from another civilization is profoundly different from an unconscious machine, even if their actions are indistinguishable. Let me return to the scientific method, the process that has guided human inquiry for centuries and that must guide us now. The method is simple in principle but demanding in practice. You observe a phenomenon. You formulate hypotheses to explain it. You make predictions based on those hypotheses. You test the predictions through further observation or experiment. You revise the hypotheses based on the results. You repeat this cycle, progressively refining your understanding, asymptotically approaching truth. The method does not guarantee success, and it does not provide answers on human timescales. It is slow, painstaking, and often frustrating, but it is the only reliable way we have ever found to distinguish reality from illusion, fact from wishful thinking. In the case of 3I divided by Atlas, we are in the hypothesis formulation stage. We have observations that defy easy explanation. We have competing hypotheses: natural comet with improbable clustering of features, measurement or modeling error despite rigorous analysis, and artificial probe under intelligent control. Each hypothesis makes predictions. If 3I divided by Atlas is a natural comet, future observations should eventually reveal some overlooked factor that explains the trajectory anomaly, perhaps subtle outgassing we failed to detect, perhaps an error in the mass estimate affecting the gravitational calculations. If it is a measurement error, independent observations with entirely different instruments should show discrepancies, and a consensus will emerge on the correct values. If it is an artificial probe, we might detect additional anomalies as it departs. We might receive more signals, or we might detect similar objects arriving in the future. The next few years will be critical. We must continue observing not only 3I divided by Atlas, but the sky in general, watching for more interstellar visitors. We must analyze the existing data with every tool at our disposal, applying machine learning algorithms to search for patterns we might have missed, conducting detailed simulations to explore every conceivable natural mechanism. We must collaborate internationally, pooling resources and expertise, because this is not a problem for one nation or one agency, but for all of humanity. And we must communicate our findings transparently, publishing data and methodologies openly so that the entire scientific community can participate in the analysis. But there is also a need for preparedness beyond the scientific. If 3I divided by Atlas is confirmed as artificial, governments and international bodies will need protocols for response. Who speaks for humanity? What message, if any, should we send? Should we attempt to send a probe to intercept it, even if current technology makes that nearly impossible? These are not scientific questions, but political, ethical, and philosophical ones, and they require input from a broad range of disciplines and perspectives. The United Nations has an Office for Outer Space Affairs that coordinates international space policy, but it has never faced a scenario like this. We may need new institutions, new frameworks, new ways of thinking about humanity's role in a cosmos that is suddenly less empty than we thought. There is also the question of public communication. If agencies confirm that 3I divided by Atlas exhibits signs of artificial origin, how and when do they disclose this? A premature announcement could cause panic, disrupt societies, or trigger irrational responses, but withholding information, even for well-intentioned reasons, erodes trust and fuels conspiracy theories. Striking the right balance between caution and transparency is immensely difficult, especially in an era of instant global communication and social media, where rumors spread faster than facts. The lesson from past events, from the panic following Orson Welles' War of the Worlds radio broadcast to the measured response to the discovery of exoplanets, is that context and framing matter enormously. People can handle extraordinary news if it is presented responsibly, with clear explanations of what is known, what is uncertain, and what the implications might be. I want to conclude by addressing directly the question that I know many are asking: do I believe 3I divided by Atlas is artificial? The honest answer is that I do not know. The evidence is tantalizing but not conclusive. The trajectory anomaly is real and significant. The pattern of features is unusual and difficult to explain with conventional models. But the scientific method requires withholding judgment until the evidence is overwhelming, and we are not there yet. What I can say with confidence is that 3I divided by Atlas deserves our most rigorous scrutiny, that dismissing the artificial hypothesis without thorough investigation would be a dereliction of scientific duty, and that the next few months and years of observation and analysis will be among the most important in the history of astronomy. I also believe that regardless of the final answer, the questions raised by 3I divided by Atlas are essential for humanity to confront. We are entering an era where the search for extraterrestrial intelligence transitions from the periphery of science to the mainstream, where our instruments are finally capable of detecting the subtle signatures of other civilizations if they exist. Whether 3I divided by Atlas is the first such detection or merely a precursor, a dress rehearsal for the real event still to come, we must be ready intellectually, emotionally, and institutionally for the implications of contact. We must think through the scenarios, develop the protocols, and have the conversations now before we are forced to do so in the midst of a confirmed detection. There is a quote often attributed to H.G. Wells, though its exact origin is unclear. We are living in a world where information travels faster than light, but wisdom moves at the speed of continental drift. That seems especially apt here. We have the technology to detect interstellar objects, to analyze their compositions and trajectories, to communicate our findings instantly across the globe. But our wisdom, our collective understanding of what it means to encounter another intelligence, lags far behind. We must accelerate that wisdom, cultivate it through education, dialogue, and imagination, so that when the moment of confirmation comes, if it comes, we are prepared not just technically, but philosophically. Let me also address those who might say that even entertaining the artificial hypothesis is irresponsible, that it gives false hope or encourages pseudoscience. I understand this concern. The history of SETI is littered with false alarms, signals that seemed artificial but turned out to be satellites, terrestrial interference, or natural astrophysical phenomena. The WOW signal detected in 1977, a strong narrowband radio signal that lasted 72 seconds, remains unexplained to this day, but is widely assumed to be either a rare natural event or a human-made signal that was not properly identified at the time. Tabby's star, as I mentioned, sparked intense speculation, but the alien megastructure hypothesis has been largely abandoned. These examples teach us to be skeptical, to demand rigorous verification, and to avoid premature conclusions. But skepticism must not become cynicism. The absence of confirmed detections so far does not mean they are impossible or even unlikely. It may simply mean we have not been looking long enough or with sufficient sensitivity. Consider the scale. There are hundreds of billions of stars in our galaxy alone, and trillions of galaxies in the observable universe. Even if intelligent civilizations are extremely rare, the sheer number of opportunities means they almost certainly exist somewhere. The question is not whether they exist, but whether they are close enough and active enough for us to detect them. 3I divided by Atlas, regardless of its origin, reminds us that the universe is full of surprises and that the search is worth conducting with rigor and openness. And so we return to the central imperative: observe. The greatest tool humanity has ever developed is not the telescope or the spacecraft, but the method of disciplined observation and logical inference, the scientific method itself. It is what has taken us from ignorance to understanding in every field of inquiry, from medicine to physics to biology. It is slow, it is uncertain, and it is often frustrating, but it works. When we observe carefully, record accurately, analyze rigorously, and remain open to revising our conclusions in the light of new evidence, we make progress. Sometimes that progress is incremental. a small refinement of existing knowledge. Sometimes it is revolutionary, a paradigm shift that changes everything. We do not know yet which category 3I divided by Atlas falls into, but we will only find out by continuing to observe, continuing to question, and continuing to test our hypotheses against the evidence. The universe does not care whether we understand it. It does not adjust itself to match our expectations or our hopes. It simply is. Governed by laws we have painstakingly uncovered over centuries but have not yet fully grasped. 3I divided by Atlas is a gift in that sense, a phenomenon that challenges our understanding and forces us to refine our models, whether it turns out to be natural or artificial. If natural, it teaches us something new about cometary dynamics, orbital mechanics, or perhaps astrophysical processes we have not yet identified. If artificial, it teaches us that we are not alone, that intelligence is a cosmic phenomenon, and that the universe is vastly more interesting than even our most optimistic speculations have imagined. So as 3I divided by Atlas continues its journey outward, moving at over 30 kilometers per second into the space between stars, carrying with it whatever secrets it holds, we must do what we do best: watch, measure, analyze, and seek truth. We must do so with rigor and humility, acknowledging what we know and what we do not know, avoiding the twin pitfalls of dogmatic skepticism and credulous acceptance. We must remain scientists, guided by evidence and reason, but also dreamers, open to the possibility that the universe is stranger and more wondrous than we have imagined. Because in the end, whether 3I divided by Atlas is a lump of ice and rock or a messenger from the stars, the act of observing it, the effort to understand it, is itself an affirmation of what makes us human. Our curiosity, our drive to explore, and our refusal to accept ignorance when knowledge is within reach. Why observe, even in uncertainty? Because observation is how we transform uncertainty into knowledge. Because every datum we collect, every spectrum we record, every trajectory we calculate brings us incrementally closer to understanding. Because the alternative, willful ignorance in the face of mystery, diminishes us. And because, ultimately, the question posed by 3I divided by Atlas is the oldest and most profound question our species has ever asked, and we owe it to ourselves, to our ancestors who first looked up at the stars and wondered, and to our descendants who will inherit the cosmos we explore, to seek the answer with every tool at our disposal. The truth, whatever it may be, is worth the effort.